Dumas was a Frenchman. He's not the same Dumas that wrote the Three Musketeers. It's a different Dumas. And he came up with a lot of methods. So when if you see reference to Dumas method, it may not be this method, but this is the method for determining the molar mass of a compound if it is volatile. So it has to be something, it can be above the boiling point of water. It can be higher than that. We're using some that are just above the boiling point of water so that we can use water that's not boiling yet. Okay, it's on its way. Actually, the water doesn't have to be boiling. It just has to be hotter than the boiling point of the compound so that we can vaporize it. Okay, let's see. Let me put today's the 10th. I think that's enough information. All right. So this method centers around two things. The same as all of our molar mass determinations, right? The definition of molar mass. And I used MW, molecular weight. The method uses a big M for molar mass. The reason I don't use the big M is it looks like molarity. So molecular weight, and that comes from my childhood as a student. We call it molecular weight then, even the professors did. Is the mass in grams divided by the moles. So we need to know these two things. What's the mass of that gas? How many moles does it represent? And this is one of those methods that you can use, that is used, to find the molar mass of a compound without knowing anything about it. So when you've got the percent composition, and you can find the empirical formula, then the next step to the molecular formula is you need to know the molar mass. But if you don't know the structure of the compound, if you don't know the formula, then how do you get the molar mass? Well, this is one of the ways you do it. Right? There are several others. They're colligating properties. In other words, they don't depend on the identity of the compound. This doesn't matter what the compound is. So this is our end game. But since we're dealing with gases, we're going to use the ideal gas equation to help us. EV equals nRT. So if we assume that R is this value, with these units of measure, right? Volume, pressure, moles, temperature, then that dictates what these must be. No matter what you measure them in, they have to be converted to these units before we can use them. So you can use this to find out how many moles of gas are in your container. And our container is a 125 milliliter Erlenmeyer flask. So that's going to confine our gas. And you need to know these values, right? And you can solve for how many moles and then substitute in here. Or you can convert this or solve this one for moles, right? PV over RT, and then substitute that in here. So now the molecular weight is equal to mass divided by that monstrosity. And then if we flip it around, like the denominator of the denominator is the numerator. So we just flip that. Now we have mass times R times the temperature in Kelvin divided by pressure in atmospheres and volume in liters. And if we get all of these values, we can solve for the molecular weight. Okay, so how do we do it? Well, you need to be able to find out the mass of the gas and how many moles it is. So how do you find the mass of your gas? Well, you have your Erlenmeyer flask. Here. And it says it's nominally 125 milliliter flask. But that just means there's a mark on here that says 125 milliliters. Right? What's the actual volume of that container? Because what you're going to do is you're going to put some of that liquid in here. Actually, you're going to have two aluminum foil caps. Why do we need two? One of them is going to go on like this with copper twisty on it. That copper, that aluminum, and this flask together are the tare weight. That's without your compound. Then when you put the compound in there, you put the cap on there. So what you would do is you would take this and that and that and just separately put them on the balance and get the tare weight. Then when you put your, 3 milliliters of your compound in here, then you put this cap on there and tighten it up real good and bring that aluminum foil right down to the top and try not to push it in. Try to make it flat across there. So when we go to find volume, I'll tell you in a minute, then you know where that aluminum foil was sitting. Then you put another sheet, a bigger sheet of aluminum foil over that. And you hold that together with a rubber band. Okay, now why do we do that? We're going to stick this thing in boiling water. Right? And what does steam do? It condenses on cold surfaces. We can't submerge the whole thing. So we've got a clamp holding it. Submerged in the water. Otherwise it'll float. So we protect this inner aluminum with an outer aluminum. Only that outer aluminum is not included in the tare weight. So by protecting the inner aluminum, once we get finished vaporizing all that compound, and it goes out through a little pinhole that you poke through both of them, then there's nothing in here but the gas, the compound, the vapor. Right? Once you've done that, then you pull it aside and let it cool down. And when it cools down, whatever vapor is in here is going to recondense as liquid. But it's the same mass as it was as a vapor. Right? And you have to assume that the liquid that condenses has an insignificant effect on the total volume. And with our measuring techniques, that's true. Okay. So once you've pulled it out, once you've converted it all to vapor, and you pulled it out of the hot water and swung it aside and let it cool down, and you get ready to weigh it, you take that outer aluminum off. That's protected the inner aluminum from condensation. And you inspect it to be sure you didn't have some leaks. You get some condensation in there because that will bias your data. And then you leave that inner cap on there. And you take a paper towel and be sure it's dry wherever you can soak up water. Once it's set, hey, oh, I was doing, you've already been here before. Yeah. You've seen this one before, besides it'll be recorded if you need it. I was just giving them a rundown on the method. So once you pull it out and it's cooled down, you take that cap off, be sure it's dry. Then you can stick it on the balance and get a weight. Try to get 3 decimals if you can. If you can't, that's all right. Because our thermometer only gives us 2 places anyway, if you're lucky. Okay, so now you have the weight before and after. You just subtract the final weight from the tare from the final weight. You got your mass, the gas. Okay. Now, what's the temperature of the gas? Huh?
Whatever it goes from.
Yeah, it's the temperature of the water. Right? So you measure the temperature of the water, and that gives you this. Plus, you've got to convert it. Plus 273. Okay, got that one, got that one. What's the pressure? Read it off the thermometer. And you have to convert that to atmospheres. It'll be in millimeters of mercury, so you divide it by 760. And then the volume. So how are we going to get the volume of that thing? You have 2 choices. Either way, you're going to fill it up with water. Right to the rim where the aluminum was. And then you're going to weigh it. That's one choice. Weigh it and the aluminum and copper wire. Right? Because that's your tare. You want to know the mass of the water that's in there at that exact level. Then if you know the mass of the water and you know its density, which is given in the method, density is mass per unit volume, right? So if we divide that by mass per unit volume, which is equal to density, then the masses cancel and you're left with volume in the numerator, right? And that'll be in milliliters. So that's the volume. And it should be somewhere 140, 145 probably. Right? Because 125 is here, you got extra. Or once you fill it to that level, pour it into a graduated cylinder. Well, I left one out there for you if you want to do it that way. Pour it into the graduated cylinder and just read the volume. Okay. So those are your 2 choices. That gives you volume. You got volume, pressure, temperature, mass. R is a constant. We can calculate. Just have to be sure your units are correct. Okay. Now, the method lists 6 liquids. I've learned from bitter experience that 2 of them don't behave very well. Right. The more volatile ones, pentane and hexane. I've pulled those out. So you've only got 4 to choose from. And they tend to behave fairly well. That would be acetone, methanol, ethanol, and 2-propanol. What's that? It's also called isopropanol. Rubbing alcohol. Okay? 2-propanol is the proper IUPAC name. Isopropanol is what they call trivial name. All right? So you can pick any one of those, just make note of the number in your report, and then compare your value of molar mass with the chart and see which one you think it is. Now, most of my students like to sniff stuff, so they smell it and see if they can figure it out that way too. And that's okay, but you still have to report this experiment to prove it. Okay. Noses can be deceiving. All right, any questions? How's that water doing? Is it going? Okay. It's okay.
Sorry, I'm sorry. I'm sorry. Just wait for me.
Here we go.
I'm sorry.
Number 1, what happens to a real gas? such as nitrogen, as it cools from room temperature to 0 K. What happens to it?
That's
Definitely turns liquid.
that cool. It goes liquid into a solid. And then
More than likely.
because it's a real gas, as the temperature decreases, the volume would also decrease until
Oh, if it were, would you expect it to disappear when it reached absolute zero? If it were an ideal gas, yes. As a real gas, no. Because it has real molecules in there. And they occupy volume no matter how small they get. The only way you can make a gas occupy less volume is decrease the distance between the molecules. Molecules have a definite volume. Ideal gases don't. The molecules in an ideal gas are point volume. Okay. How about 2? What are the units of universal gas constant R? Well, they can be several, but the one we used was what? I'll put the number in. So what are the units?
atmospheres, liters, moles, and Kelvin.
Uh-huh. Why do we need to know that? Because that tells us what the units are in the rest of the equation. Okay. And 3. Water freezes at 0 degrees Celsius, 32 degrees Fahrenheit, 273.2 degrees K. Which one is correct? Or which one is colder? Oh my goodness. Oh my goodness. You seen those old Saturday Night Live with, what was her last name? Lorraine Newman, I think it was. The skinny chick with frizzy hair. And she played Reagan from The Exorcist one time. Did all kinds of mean stuff to Richard Pryor and some other black dude. And she would go, oh my goodness, kind of like Shirley Temple. Oh my goodness. That's what I think of when I hear that. Okay, so they're all the same. Right? Just different units. Just like I've always said, nature just does what it does. And we slap these units on it because that's how we understand it. Okay, 4. When can a real gas behave as an ideal gas? What are the conditions? And are they met in this experiment?
No. Very low pressure, but very high temperature.
Right. Pressure low, temperature high. So are they met? What do we mean by low pressure? 1 atmosphere, and we're less than that. Or even, you could go up to 20 atmospheres and probably still be hit out together. Once you get up to 50 atmospheres, then you need your correction factors. How about temperature? What do we mean by high temperature? Relative to what? Relative to 0 K. Right? So 273, or in this case, closer to 300, right? 300 K, that's high temperature. So the conditions are met. And then the last one, it looks like 5, needs a calculation. A gas with a mass of 33.62 grams. So the mass equals 33.62 grams. And a volume of 10 liters. A temperature of 27 degrees C. And a pressure of 730 torr. What's the molar mass of that gas? And then which gas is it? All right. What about the units here? Those are good. Liters. Temperature? Yeah, 300. Okay. How about this one?
605.
Okay. Let's see. That should be everything we need, right? What was the equation? Molecular weight equals mass times R times T over P times B. So 33.62, 0.08206. I better write on this side so they can see me there. 300 divided by 0.9605 and volume 10. Okay.
Calculator.
Is it glitching on you?
Yeah, every time I press a button, the screen just goes dark.
Oh. Does it need batteries or is it solar powered?
I put some in before the semester started, but
Before the semester started. Somebody else is doing it.
I'm just checking. I don't feel like I'm not calculating.
got 86.2.
That sounds reasonable.
Yay, I know what to do next. I know what to do next.
Okay, what is it? It's a. Go. That's the last one. Now the other questions, I guess I better let you guys do them yourself.